So let's start with Professor Shinichi Hirai. Professor at the Department of Robotics at Ritsumeikan University in Shiga, Japan, director of the Short Robotics Lab, Hirai Lab, and he investigates robots with novel functions brought by soft materials and its related technologies, including soft sensors and actuators. For the last 30 years, he has been in such university, but he was also visiting researcher at MIT, right, and assistant professor at Osaka University. So he has many papers, many awards, and I'm pretty sure that, well, we're going to be delighted with your presentation. So all room yours, and thank you very much for joining the conference.
Thank you for the introduction. Okay, so, the microphone? Oh, yeah, here. Okay. Thank you for the introduction. So my name is Shinichi Hirai, from Ritsumeikan University. First of all, thank you very much for the organizers to invite me to this fantastic conference. Okay, now I'm talking about non-electric soft robotic hands for underwater grasping and manipulation. So, okay, but first of all, let me talk about a little bit my university. I'm now in Ritsumeikan University, one private university, originated from Kyoto. Now, I'm not in Kyoto now. I'm in a Biwako Kusatsu campus. It is next to Kyoto. 15 minutes by train, very close to Kyoto. And also the Biwako is the name of the lake. It is the largest lake in Japan. So very beautiful, surrounded by mountains. So now, almost 30, just 30 years ago, our campus was established, and also soon the Department of Robotics was established in 1996. I was involved in the Department of Robotics so far. Okay, so now my lab, the soft robotics lab, we are now investigating robots with novel functions brought by soft materials. The soft materials and soft structures. And also we are working on the related technologies, including soft sensors and soft actuators as well. So today, I'm talking about the manipulation of living organisms. We are now developing the various soft hands for grasping and manipulation of living organisms. So I will introduce our works. Okay, the background, we have many grasping and manipulation of underwater organisms. In fishery, in sampling, and also and so on. And also in aqua museum also, we have many such kind of operations. In such operations, we need robot hand, okay? But electricity, you often use the electrical motors to drive the open and close robot hand. But the electricity in water often causes several problems. That's why now we are focusing on the electric-free hands. I mean, the robotic hand, without the electric driving. Okay, so to do so, first, we just here's this from Wikipedia. We just categorize. We find that we find the living organisms in water can be categorized into the newton, plankton, nekton, and benthos. We have tried to develop the robotic hand for these categories. Our idea is to use the environment around the living organisms. Okay, we now here focus on the benthos, living creatures, on the bottom, near near the bottom of the sea, and the plankton, the drifting in the water. The idea here is to use environment so the around benthos and the plankton. So the here, the benthos, we so the focus on the contact because so they are so living in so the near the on or near the ground, so the bottom of the sea. So the if you have so the something so the approaching the benthos, robotic hand make contact with the, so the bottom of the sea. So the why don't you use the contact to drive so the robotic hand? And plankton also, okay, that's so the drifting in water. So the if you so the approach robotic hand near plankton, water so the pressure, water resistance may cause. So the idea is to apply water pressure, water resistance to drive robotic hand. Okay, so let me here. So I'm talking about so the first so the contact driven hand, and so the origami membrane hand, and also water pressure driven hand. For these so the living creatures. Okay, but first of all, so we are now for the focusing on the benthos, so the living so the organisms, so the on was near the bottom of the sea. So to grasp so the such so the creatures, living creatures, we so the developed so the contact-driven hand. So it uses we have so here we have a robotic hand, so the back ones, so the consistent of so the several fingers, and also you have so the now so the kind of the object so the on the so the table. So the idea here is to open and close. So using the contact force, so the finger contact with the so the touches to the ground. Okay, so let me show the motion behavior of this hand. Okay, here, okay, now closing, opening. Okay, here we have no actuators, no sensors in the so the hand, fingers, just so the only so the mechanism. So of course so the hand is so the moved by so the robot manipulator, but so the open and close are driven by realized by the contact with the ground. Here, okay, so here like this, and also the closing, on opening, also that's so the driven by the hand. Okay, so this mechanism is quite similar to also the such as a pen, you know. So we can so push something. Okay, so we have also the another so state, and then push again. We have also move to also the original state. So this is so-called also the bistable mechanism. So we have so apply such kind of so the principle to this robot hand, to this robot hand. Okay, so structure is very simple. So it consists of two parts mainly. So first here we have so this one. So this is so the link structure. So several so the links are connected. So in series, and also we have so the elastic. So kind of so the plate here, and we have also in the top here we have also kind of also the hole, and also hole here, and also a protrusion part here. So, okay, so in open state, okay, like this, so we have also it's a connected part, so the link structure here, and so the elastic, so the sheet here. So if you push, that's so this, so if the finger contact with the ground at the top, so oh, it's quite difficult to control the position. Okay, mouse. Okay, so this part. Okay, so okay, you have to push this part. Okay, so this part moves upward. Then we have the hole here. Then we have also here. So there's some kind of nail here. This nail is inserted in the hole. This is a closed state. And also, if you have push again here, this part, slide from the so the hole. Then so we can so the open the finger. So the okay, so they have a protrusion and also the notch. So the based on this, so the structure, so we have a so the just by contacting, so we have a so the kind of straight so the state and also the curved state. Curved state can be so realized so the through the contact. So they are so the driven by so the contact. So here is a more so detailed one explanation. So but first we have so the closed. Sorry, it's an open state. So it's straight. Then so here. So if so the finger is pushed, so the finger is contact with the ground. So this part so somehow so the inclined. Then so the nail is inserted in a notch. Then so again so if you this is so the locked state. So again so if you have contact, then so here. So this so the part so again so moved up. Then so this is the protrusion part. So it pushes this so the sheet. Then so this so the nail so is so now free state. Now so this is an open state now. Again. Okay. So also unlock so we have a so in the so the reverse state we have a so unlocked state now. So this is so the first prototype. So the robot hand. So we have so maybe 8 so the fingers. So also the fingers are driven by the contact forces. So this is kind of so the simple experiment. So this is so the sample of a so jellyfish. So made of so the gel. Okay, so again, so here. Just pushing. Okay, now open. Just pushing. Now it's closed. Again, pushing. It's open again. So we can so the transit so from so the open, close, and close to so the open states. And also we have as experiment so here. And this is not also the living organism, but a pudding. Okay, you can see here. Some are so broken, but anyhow, so we can so the glass bit, glass pudding, and also the release the pudding again, like this. Okay, again, so we have no actuator in this hand, no sensor, no actuators, no sensors, just as we have also the mechanism, locking and unlocking mechanism alone. And also we can so grasp many things, octopus egg, again, like this, and so on. Okay, so this is another one. Okay, here you can see here, so because of the fingers are made of so this is a failed one. So sometimes so it fails because of so sometimes so here. So this is somehow so broken. It's so hinders that's so the opening. So because of now so the initial one so consists of the rigid rings connected by bolts and nuts. So it's somewhat complicated. So we have simplified the fingers. So instead of so rigid rings, we just so replace the rigid rings. So by so flexible link. So also so this is so printed. So using 3D printer. The principle is same. So but so it works well again. So here. Now so the more simple. So the structure is very simple. So now it consists of 2 parts. Okay, so also both are for the 3D-dimensional 3D printed. Oops. And also Okay, so this is so the can grasp some so the much thinner. This is the vegetable. So the okay, so the because it is the curve, so the inside. So the once we have so the contact with the ground, so it can scoop out. That's so the such kind of so the thin target like this. And also, okay, we tried many of the experiments. This was the sesame. Because of the, we had designed so the finger shape. So okay, so in the open, in the, so the closed state, now we have a so the small gap between neighboring. Okay, like you can see here, in the closed state, we have a so the very so the small gap between the neighboring fingers. That's why so we can so the pick up such kind of so the granular materials also. This. Okay. Okay, so this is so the contact, so the driven robotic hand. Okay, now so the want to so the step on so the focus on the plankton, so the drifting in the so the water. So the idea here is to use, first of all, so the again so the scoop, so the such kind of plankton, so the with water. So the we now so here so we developed so the origami membrane hand. Okay, you can see here this so the hand so consists of so the origami so the membrane driven by also the contact based so the mechanism. So the idea here is so just by enveloping so such kind of origami membrane, we can so the grasp a plankton with water. So the idea is spoken bodies with liquid. So here, okay, of course you can use so the ladle, but so it often so the moving, so the sometimes so the water drops, and also water flow, so the there are in this case beads, planktons. So that's why so we developed so another approach, so to membrane based so the hand. Okay, so this is so our so the origami membrane hand. So it consists of so the origami membrane below, and also the vessel, so the upper part. Okay, so if you so in this open state, so the left, right side, right, we have this is a closed state. So just so pushing down the top plate beneath. So okay, this is closed. We can so close the hand. So here we use as a cresting pattern. So it's a famous so the origami pattern. So it's so like this. So we can so here the open state, so the closed. So we can move, we can deform, such kind of pattern like this, from the polygonal prism to a plus shape. So we have the fabricated membrane, so via using the liquid silicon printer. So here this membrane was made of the silicon, so liquid silicon. So it's based based strong. So even if you have printing by hand, it doesn't it can stand. So by human such kind of motion, human such kind of forces. And so here we have so the these are the lines are so the fault lines. So you can so the print out so the such kind of structure using so the 3D printer. So like here, so the again, so the this is so the motion, deformation of the membrane. So in the open state, okay, this is so the bottom so the face. In the open state, so we have a so the hole, so at the center here. But so once so it's closed, deformed, so the bottom is completely so closed. So okay, so we can so keep the water, so inside the membrane. Okay, so here, so we're now testing, demonstrating. Okay, now we are so picking floating bead with water, and so placing so right so vessel like this. Again, here also we have used the contact so driven so the structure, so to open and close the membrane. Okay, so the difference you can see here. So we have basically no so very little so water so drop, and also we have so small disturbance to the so the floating bead. Okay. Okay, but here, so this one, but so here, in this one, so we are now using so the contact base, so again, so the contact base, so contact-driven mechanism. It means that so we can so apply so this structure, so near the bottom, so in water, so I mean so far from so the bottom, so we cannot apply this so robotic hand at all. So that's why so we have so also developed another so robotic hand, so the plankton to apply to use so the water pressure, water resistance to drive the hand. So this is so the motion. You can see here. Open and close can be so performed by just by so during so moving down, so moving down it opens, and so if you so move up, so the fingers are closed. So this is caused by so the water pressure. Okay, so the idea here is okay. We have so the water resistance panel, and so we have a finger, elastic finger, short fingers, and also we have a base here. So the base and so the panel are so are isolated, so they connected by so the elastic fingers. So okay, if you so apply force so to the panel from upward, then so the fingers will so bend inside. Then so we apply so the locking mechanism also so at the tip. So then so we can so lock that's so the fingers. And also in air, again, so in contrast, so if you have air, so we have such kind of so closed state. Then so if you so moving down, so then so now so the force so upward is applied to the upward. Then so this so also so this so the force will so open the fingers because so so the resistance panel, so the will so the moving up. So the and also so the this is kind of so the principle of the open and closing the fingers, and also we have so designed so the locking mechanism so the at the tip of the so the fingers to ensure the so the closed state. So we have also the kind of such kind of a structure. Here we have also the concave region and so the protrusion at the tip of the fingers. This was the this was the kind of so the animation here. So the once so the fingers meet one another. So the finger, the tip will so the protrusion will so the guided inside the so the concave region. Then so it will so the locked so the in the so the such kind of round so the round region. Then so the we have also the locked so the state here, and also so the then so in this so the locked state. So the if so the we so the somehow so the twist that's the plate, so we can so the easily so the unlock that's the fingers. Then so we have also the putting so the rotating plate on one side of each finger to realize such kind of so the twisting motion. So this is the prototype, so the finger part, so we have the elastic finger, also so the printed in a, using so the silicone rubber printer, and also a locking mechanism, so and also the rotating plate, so they are so they put so to the tip of the fingers. So this is so the tip of the finger. So somewhat complicated, but so anyhow, so we have also the locking mechanism, blue one, and also the rotating plate to so the twist the fingers to unlock the fingers. Here's the base and so the water resistance panel, so the upward. That's so the group itself. So the base and so the water resistance panel, and so the fingers, and at the tip, so you have also the mechanism, locking mechanisms. So here you can see here, here. At the first time is open and close, open and close. So just pushing down to the open, so the moving up, so this so the closed. Here experiment setup. So here we have also again so the put this finger robot so on the top robot. So we have so the conduct experiment here. This is open and closed and locked. So like this. So now so the fingers are locked. So one another. And so just so the moving down quickly. Then so we can so the open the finger. So we are using such kind of water resistance to open and close the fingers. And also, we find that so in this case, so in this hand, so the velocity is very very so critical to realize so open and close and locking and unlocking. So if you have so the appropriate velocity, we can so successfully lock the fingers. But so if the velocity is slow or kind of fast, it doesn't work. So it depends on so the structure. And this kind of experiment, so we have also something target in the water. Now so it can so pick up successfully. But unfortunately, in this case, we cannot release it. So this is because the target weight. So the affects the result. We have the lighter one object target. So we can successfully release the object target like this. So now the depends on not only the speed but also the weight of the target. So now we are analyzing this phenomena. So by using the mechanical analytical model. Okay, so here, here we have introduced the robot hand, the grasping, the underwater organisms, the contact-driven fast one hand for benthos, and the origami membrane hand for plankton near bottom, and the water pressure-driven hand for plankton. So now we are analyze. We are now redesigning these hands to realize more stable grasping and releasing. And also they were now analyzing the behavior of this hand using the physical models. Okay, that's it. Thank you for attention.
Okay, so thank you very much for the next presentation. So we have time for some questions. Have some of them. Not sure if. Okay, maybe I can start. Well, I have several questions because this is quite interesting. So my first question is regarding the design of all these systems. In the end, you have many instabilities, right, to induce actuation, etc. How do you design that? Is trial error, or do you have some computational models, something like that?
Currently, it's a trial error. So we have basically we have the design, we have first design, kind of first prototype, we test it. Then we find out kind of the stability or kind of the performance.
Okay.
And also stability. Then the design, that's the finger. Also, we're now building the mechanical model, analytical model.
Yeah.
And we are doing the computer simulation as well. But it requires much the time now. So that's why now mainly we are now using kind of trial and error approach.
Well, I think you should meet these guys at some point. They're going to present tomorrow because they have a nice spy.
Oh, okay.
Really nice method. So, any question from the audience? Okay, here, Fabrizio. I have more, but.
Thank you. Really fascinating talk. I have a question related to the last device that you showed, and probably is slightly linked to the comment about the instabilities. Have you noticed any specific effect given by the speed of the impact to the water in terms of really of efficiency of the device?
Yeah, actually, you're right. Here, we have tested how the velocity, how velocity affects the locking mechanism, and also unlock also maybe the impact with also the affect this unlock mechanism. But we have not tested in the preliminary level, in a simple level. We have not talked now here. But yeah, you're right. The impact, the complete effect, unlock the behavior.
Just commenting on that, I think this is quite interesting because you will have two different mechanisms. So first the impact, second viscoelastic effects. Viscoelasticities, essentially the materials have different stiffnesses and there's different actuation rates. So in the end, you have some relaxation that can introduce some shift into the instability. I think this is kind of super nice area to explore. Any last question from the audience?
I have one.
Sure. Let's go.
Okay.
Part of the audience, right? Well, very inspiring. Thank you very much.
Thank you.
So you don't think you should integrate any type of sensors or for instance, right, to improve your mechanisms?
Okay. Yeah.
So
yeah.
where is the limit
Okay.
if you think there is a limit?
Okay, so it's kind of a sort of extreme. Okay, it's the first step. So we have no sort of no actuator, no sensor. Okay, it's one sort of idea, one kind of, but sort of kind of extreme. But sort of course, if you introduce sort of sensor, what kind of simple mechanism, for example, so the kind of sort of water pressure sensor or something, and so the mechanism sort of driven by water pressure, might be sort of improve the stability or kind of sort of opening and closing. So yeah, right. So and also now currently also kind of MEMS based, for example, MEMS based kind of structures are available. Now we want to apply such kind of small mechanism here. Then I feel not sure, but I feel it can improve the
Very nice.
performance.
Okay, thank you very
Thank you
much.
much.
Okay, so please thanks again our first speaker. Thank you very much.